Okay, so like, how many pieces of cheese do you think should go into the typical cheese sandwich? Like 2?
I don't know about 2. 2 actually seems too much
Yo,
for me.
guys. Look at this.
1 plus 3.
Huh?
I was told about this really cool physics experiment. You want to try it out?
Yeah, sure. But what the heck do you have in your hand?
It's a cup with strings attached to it, so you could spin it around in a circle.
What do you guys think will happen to the water? Do you think it'll fall out?
No, it'll obviously stay in the cup. Simple.
I don't trust you. We should test it out.
Alright, who gets to spin it?
I guess I'll do it.
Let's do it.
Alright, let's try this out. Whoa.
Ha! The water stayed in the cup. Guess you were wrong, Nelson.
Wait, but how's that possible? If you think about Newton's second law, we know that there's no force because there's no acceleration. Speed is constant, isn't it?
Well, you are right in the speed is constant, but what isn't constant here is velocity. Speed consists of a magnitude, while velocity includes both magnitude and direction. What you find that's staying constant here is the magnitude, but the direction is constantly changing as we see inside of its circular path. The reason why is because the velocity is tangential to the circular path. Perpendicular to this, there is an inward force that is responsible for changing its direction.
Oh, so you're saying the hand always applies a force to keep the cup spinning in a circle.
That's correct, and that's the reason why we have this type of circular motion. The one thing this does not explain is why the cup and the water inside of it don't come crashing into the center.
I think we can explain this using inertia. When the cup is spinning around and it's above your head, gravity is trying to pull the water downwards, but the motion of the cup actually prevents that from happening.
So what do you mean the motion of the cup? Let's say if you have a cup that's rotating clockwise, let's say, and then you cut the string at this point, wouldn't the cup just fly upwards?
Well, no, what you have to remember is that the velocity is tangential to the direction of the circle's motion. So what ends up happening is that it will continue on the path until the centripetal force acting on it is removed. This will result in the object continuing in only one direction, which in this case, since it's perpendicular to the acceleration and the force applied, would be to the right.
All right, cool. Let's try it without the water.
Well, I'm sure glad that we ditched the water for that trial.
Wow, you're right. Oh, it's all starting to make sense now. I heard there's a centrifugal force that prevents the water from falling down from the cup.
Well, actually, the centrifugal force doesn't really exist, except from the perspective of the water in this case. So, from an observer's perspective, it doesn't exist and it can't be a real force. It's only a pseudo-force.
What can be causing this force?
So what's actually happening is that the centripetal force is changing direction as the cup and the water spin around in a circle. So, although it's continuously pointing towards the middle, the start point of the vector will change as it moves along in the circle. So, what this means for the water is that the cup is continuously colliding into it and pushing it along.
Well, that makes a lot of sense, yeah.
Yeah, it sure does. I've learned a lot from this experiment. What a cool phenomenon.
Okay.